Like if I'm doing a presentation, you can't see it. Or if I have a different application open, you can't see it. Okay, so here we are rolling. Here we go. So in Calc 1, you should have been exposed to something called the fundamental theorem of calculus. It should at least sound familiar. And certainly sounds important, right? Okay, well it is. Okay, so it is incredibly important. And it's really the kind of the pinnacle of the Calc 1 course, or should be kind of the culmination of everything you did in the entire Calc 1 course. And there's an associated equation with that. All right, so there's this equation that's associated with the fundamental theorem of calculus. Okay, in Calc 2 is a whole lot about integration or integrals. Okay, does the fundamental theorem of calculus have anything to do with integration or integrals? Yes or no? Yeah. Sure, right? So looking at that equation, you see an integral, right? Where's the integral? On the left, right? The left side of the equation is an integral. So because Calc 2 has so much to do with integration, integrals, and the fundamental theorem of calculus is basically about integration, we want to start the class by really breaking this down and really understanding what this is all about. Some of you in your Calc 1 course may have done that. Others may not. To you, so there may be many of you who this is just another equation that solved another type of problem. And you were given some numbers or given a situation and you used this to crank out answers and you did several examples like that. Okay? But this is rich with many layers of meaning. Okay? And if this is the fundamental theorem of calculus, we want to know that meaning very, very well. Okay? So we can know what integration is all about and not just have it be just another problem in another chapter, another set of exercises that we can do. Okay, so we want to really dissect this and get down to the brass tacks of what this is all about. So we're going to take some time, a couple days, to kind of maybe build this up from scratch, which maybe you did in Calc 1, but very possibly many of you did not. Okay? So we better know what this is all about if Calc 2 is going to be a lot about integrals. All right, so I've kind of broken it up into several principles, okay? And so this is going to be, we're going to spend the next 2 days or so, 3 days, making sense of the fundamental theorem. And before we get to the main principles, we're going to start with principle 0, okay? Principle 0, which is about variables. Variables vary. So when you see this equation, 2x minus 7 equals 0, what do you think? What do you think about that? X is 3.5. Is that what you thought too? You were raising your hand. No? Something else? Don't worry about it? Okay. Did anyone think X is 3.5? Could X be anything else? Could X be a different value than 3.5? Yes or no? Some saying no, some saying yes. What's that? We can, but then it would be a false statement. Okay, so suppose that very same x is defined this way. Suppose that x that we were talking about is the number of hours elapsed since your plane left the ground. Number of hours gone by since your plane left the ground. What could x be? What values could x take on more than one value? Yeah. How many values could it take on? Lots and lots of values, right? It could take on 1/10 of an hour. It could take on 1/2 an hour. It could take on 2.1 hours, 3 hours, 4 hours, 4.7 hours. In fact, it could take on any real number. Could it take on negative 0.5 hours? No. He says no. She says yes. Why yes?
Because that just means the time before your plane.
Yeah, that'd be like 30 minutes before your plane took off, right? If x negative 0.5 you could just think of that as some amount of time before you took off. Okay, so yeah, so x could be any real value, and then now qualifying, saying 2x minus 7 equals 0. Well, that's just identifying maybe a specific situation. Maybe this equation then tells you how many hours until you got your first bathroom break or something like that? Yikes, right? So x equals 3.5 in this very specific situation, but it doesn't mean that x can't or would not be other values. Okay, variables vary. That's the point of variables. When you solve for a particular equation, you're finding particular values of x that make it true. X could take on other values. It just makes the statement false, just like he said. Okay. What about the variable dx? So based on x, we have another variable called dx. What's that about? The derivative of x. But no, I'm talking about, it's not, x isn't a function, x is just a variable. Yeah. Yeah, so it's a change in x. So it's a change in x. So if I were to say dx equals 3.5, how is that different than saying x is 3.5? How is that different than saying x is 3.5? X is 3.5 means amount of time since the plane took off, right? 3.5 hours since the plane took off. But dx equals 3.5 means? What's that? Is that the rate? Yeah, so what does that mean? Change in x.
At this point, it's changing as 3.5.
What's that?
At a specific point, it's changing as 3.5.
Yeah, so like we could we could talk about like an x initial, say like 2 hours. And then we could think about starting there, we could think about a change of 3.5 hours. And what would that look like when we were all done? Then x would be 5.5. So a change of x could start at any x value. It could start at 5 hours. It could start at 5 hours, and then you have a change of time of 3.5, and then now your x value would be 8.5 hours. Okay? So this dx is a change in hours. And then dx is a variable itself. We could say dx is 0.2 of an hour. Okay? Dissatisfied customer? Did you see his face when he walked out? It's not that bad so far, is it? Okay. All right. So, wrong class. Wrong class. Okay, so 0.2 hours. So if we were, 0.7 hours into the flight, and then dx was 0.2 hours, that would be the time duration from 0.7 hours into the flight to 0.9 hours into the flight. So dx is a variable as well. It could take on different amounts of change, right? Different amounts of change in time. Okay, so that's backdrop. So we really want to think about, in this course, variables, they represent quantities that change, right? That change, and so that variable takes on all those different values of that quantity as it changes. Okay, so now principle 1, rate of change. Rate of change. So let's do a rate of change 101. Here we go. So we're going to buy trail mix that costs $3.20 per pound. And we're going to scoop some into our bag, and then we're going to decide we want some more. What additional cost will you pay for 1.5 more pounds of trail mix? I want everyone to figure out what that value of that number is before we talk idea and meaning. Just figure out. Answer that question. Figure out what that amount of money is. Go. Everyone do it. You need a calculator? Get a calculator? Hopefully you don't. But everyone figure out what additional cost will you pay for 1.5 more pounds of trail mix. Okay, so starting next week, I'm going to have a list of your names. I'm going to learn your names, and we'll be calling on everyone. We'll get their chance to speak out. So now I'm just going to point and ask what your name is. Let's see. How about In the red shirt. Yeah, it's red. What do you think? Did you figure it out?
I don't want to make myself look like an idiot, but it should be $4.80.
And how did you do that? How did you get $4.80?
Which is I took half of $3.20 and then I added it to the full cost, which is $3.20 total.
Okay, so yeah, you went a little more in depth than I was looking for. So you were explaining how you did the calculation. What calculation did you do?
Rate.
So when you took one and then a half more, what were you doing? Multiplying, right? Yeah, you took 320. Yeah, you just explained how you multiplied, right? So 320 times 1.5. $4.80 additional for the additional amount of trail mix you put in, right? Okay. Now, so we know calculus is not about numerical computations. There's symbols everywhere, and these symbols have meaning, okay? And so when we have real-world situations, we're going to model them with calculus with symbols, and so we're going to practice that, okay? So we're going to define each variable below completely and precisely with written words, okay? And we're going to decide if it's known or unknown in this situation. So here's a list of variables: x, y, dx, dy, and m, okay? And so each of those variables, you want to write out a phrase that describes the meaning of the quantity that it represents, and then decide, is that a known quantity or unknown in this particular situation? Do we have a particular value for each variable given the setup? Okay, so I kind of have to give you the first one because you could do it either way. So what is x? X is going to be the total number of pounds of mix in your bag. Okay, so if x is the total number of pounds of mix in your bag, what would y be? What would dx, dy, and what would m be? M. And so by m, I'm going to mean the constant rate of change. Okay, so go. And if you need to confer with the person next to you, two things: a written phrase and whether the current value in this situation is known or unknown. Go. Okay, you've got a chance to think about it. Now find a partner. Introduce yourselves if you need to. Compare with the person next to you. Go. Find someone to talk to. Okay. Okay, let's see how you did. Here we go. Okay, how about back here in the green check shirt? How'd you do? What'd you think Y was?
The number of dollars spent. Total number of dollars spent.
Yep, the way I worded that was cost in X pounds of mix, right? So yeah, number of dollars, total number of dollars spent. On a roll, what is DX? What did you say DX was?
The change in the number of pounds.
Good. Change in the number. That's exactly what I wrote. Change in the number of pounds. Okay? Are we doing good so far?
Yeah.
And so take over from here. What did you put for DY? Yeah.
The change in the cost of the total.
Change in the cost. Okay. And so I told you that M was the constant rate of change. So let's go through whether known. So is the total number of pounds of mix in the bag known or unknown? Do we, in this refreezing time, and we're looking at the situation, do we know what X is? People are saying no. Okay, I'll go with the consensus. All right, what about Y? Do we know the cost of X pounds? No? What is it? The cost of all the pounds in the bag. Do we know what that is?
No.
We do not know that. How about the change in the number of pounds? What is that? DX is, in this situation, 1.5. What about the change in the cost? 480. Okay, and then do we know the constant rate of change? Yeah, it's right there. Okay? So then what I want you to do is we started off by saying what additional cost will you pay for 1.5 more pounds of trail mix, and we came up with this. So now I want you to reproduce this calculation with the symbols that we chose. So with the variables that we chose, what equation represents how we solve this problem? What equation represents how we solve this problem now using the symbols that we chose? How about in the green shirt right here, the dark green shirt? Yeah, you were going to raise your hand. Yep.
It would be dy equals dx times n, dxn.
Okay, so he wants dy equals m times dx. Agree?
Yeah.
Exactly, right? So we said at $320 per pound, any number of pounds is going to what? Cost $3.20 times as much as that number of pounds. This is going to be our mathematical meaning for constant rate of change right here. This is how we're going to conceive of constant rate of change. Given any change in x, the corresponding change in y will be m times that change in x. What does 60 miles per hour mean? What does 60 miles per hour mean? It means every hour you go 60 miles. Is that what it means? That's a very narrow definition, or very narrow meaning.
You go 6 miles per hour.
So just to say that every hour you go 60 miles is incredibly narrow. Can we be more?
You have to say, like, if you go at a constant rate.
Okay, yeah, that's implied. So we're going at a constant rate of 60 miles per hour.
The instantaneous speed is 6 miles.
Okay, but we're deviating from where we were going. Yeah.
For every hour, your mileage is going to be 60 times more that rate.
Right, so don't you know how far you go in 2 hours? How far do you go in 2 hours? And how far do you go in a quarter of an hour? 15 miles. How far do you go in 10 hours? 600 miles. So you know a lot more than just that you go 60 miles in 1 hour. You know how far you go in any number of hours. How far do you go in 3 hours? 180. And how did you do that? You just said, oh, my change in time was 3 at 60 miles per hour, and I know that I go, what? 180 miles. So a constant rate of change of 60 miles per hour means given any change in time, your change in distance will be 60 times that change in time. 60 times whatever change in time you have, whatever number of hours you pick, will give you the change in distance that you travel. Okay? That's a lot more powerful definition than in 1 hour you go 60 miles. Right? You know how far you go in any amount of time. That's dy equals mdx. Okay, gas is $2.25 a gallon. Gas is $2.25 a gallon. How much will you pay for 10 gallons? 10 gallons. We can do 10 gallons in our head. We can do it. $22.50, right? You just did this. You took 10 gallons times $2.25 a gallon. Additional amount you pay would be $22.50. Okay, that's constant rate of change. The total cost additional cost you would pay would be 22.5 times however many gallons you buy. So this is crucial. All right, this is our bedrock of rate of change, constant rate of change. So so next we're going to remove 0.4 pounds from our bag, and we're going to return it to the bin. After we know that no one's looking, right? So, quick, what's dx, what's dy, what's m? Go. Take 20 seconds. In this situation, what is the value of dx? What's the value of dy? And what is m? Yeah? He wants dx to be negative 0.4. Agree? Change in number of pounds. Now it's negative because it's decrease, right? Decrease means a negative change. Change in y is always m times the change in x. You can take 320 times that change in x. 1.28. 2.8. What happened? Our cost just went down, right? So that amount we're going to pay just went down. So it decreased. M is still the 320 dollars per pound. Okay, ready? Good. New situation. A soldier lowers an American flag at the top of a pole at 0.75 meters per second. How much does the height change from 0.6 seconds to 2.4 seconds since the flag left the top of the pole? We're going to do it again. Now what I'm going to tell you here is that y is the height of the flag above the ground. In meters. So, quick, can you get expressions for x, dx, dy, and m? Or written statements that define x, dx, dy, and m.
This would be time it takes to get lowered.
That sounds like just one time. So we want a variable. How can we phrase that so that's a variable
Change
number?
in time.
Is x the change in time?
No.
Okay.
Number of seconds since the flag left the top of the pole.
Okay. Yeah, so you had the right idea, but you made it sound like a particular amount of time, right? So x is any amount of time since when? Yes, since the flag left the top. The number of seconds since the flag left the top. And then we said y is the height. So then what would dx be then? That's some change in time, right? That's some change in time. dy then is change in height. And what is m? That's the constant rate of change, okay? Is it negative or positive? Okay, we'll talk about that in a second. So do we know what x is? Well, we have a starting and a finishing time, right? So it starts at 0.6 and ends at 2.4. So yeah, we know what x is. We know it varies from 0.6 to 2.4. Okay. And then do we know dx? How do we get dx? What is it? Final minus initial, right? So it's going to be the final value of x minus the initial. So it's going to be 2.4 minus 0.6 or 1.8 seconds, right? Okay, and then what would dy be? What do you want to do? Right, so we don't have to figure out what the starting height was and the final height was and subtract. We know we have constant rate of change, which means that the change in y is always negative 0.75 times the change in x. So if in 1 second it drops negative 0.75 meters, then in 1.8 seconds it's going to drop 1.8 times as much as negative 0.75 meters. And what is that? Anyone got it? Is it under the ground? Is it 1.35 meters below the ground? Why is it negative 1.35? What does that mean? Yeah, the value, so dy being negative means y is decreasing, right? Y is decreasing means that then dy, the change in y, is negative. Okay, again, making sense of rate of change by thinking of, given a change in x, your change in y is always the constant rate times that change in x. Okay, any questions on that? Yes, please.
So in this case where you're given an interval,
Yeah.
would you say x is the interval, or would you say x is just 2.4 because that's the time that's elapsed?
So you think of x as varying. So they gave us a starting value of x and a finishing value of x. So it starts at 0.6 and it varies to 2.4. Is that?
Yeah.
So in that scenario, dx takes on one value of 1.8 because that's the change in x. But that change in x, 1.8 seconds, occurs as x changes from 0.6 to 2.4. So we don't know a particular value of x, but we know where it starts and where it ends. And that it's going to vary through that from 0.6 to 2.4 seconds. Other questions? Yeah?
So I guess for this type of problem, does it really matter if we went through the dy equals mdx approach, or if we just solved it in an interval form?
So the point of this is to make sense of ideas. Don't think of this as, I'm going to see another problem just like this. Yeah, so we want to make sense of constant rate of change, and we're modeling it, right? So, but yeah, so you get the same thing with dy if you found y both ways and subtracted. Yeah. Okay. Okay, so let's look at this, and I want you to tell me this graph on the left. What does it have to do with what we were just talking about in the flag example? So I've got a scale here, 0.51, 1.52, 2.53, and then I've got this scale on the y-axis here, 0.51, 1.5, negative 0.5, negative 1, negative. Can you read those numbers? Are they big enough on the screen? So here's a graph. It's a blue line. What does it have to do with the soldier lowering the flag? So someone says the constant rate of change is the constant speed. So then what's the quantity on the x-axis here? What variable or what quantity are we talking about there? Is it the height? Meters per second. So I've heard time, height, and meters per second. What is this? I think you need a moment with a partner to figure it out. So what is that axis? What variable or what quantity is it modeling for us? And then what about this one? So what quantity, what variable are we talking about here? Go. Take a second. Okay, so let's talk about the y-axis first. What quantity is the y-axis? What quantity are we putting on the y-axis in this graph? Height. It's a height quantity. Agree? Because the height, of course, is what? Negative 0.75. Is that right? It's under the ground. That's what you're telling me. If you're telling me this is height, then you're telling me the height is negative 0.75.
That's a rate of change. It's the rate of change.
It's the rate of change. It's the rate of change. It's and as the whatever quantity on the horizontal axis changes, what happens to the rate of change? It's the same. It's constant, right? It's constant, right? So it's constant at negative 0.75. It is not the height. This is a graph of the rate of change. This is a graph of the rate of change as what? For what variable? Time, which was, what was our variable for time? X. X was the number of seconds since it left the top. As the seconds go by, the rate is negative 0.75 always. It's a constant rate. So that's what this is and so we call this a rate of change graph. Why? Because the dependent quantity, or what's being shown on the y-axis, is rate of change. So this is a rate of change graph. Okay.
Can you put one variable on the x-axis?
What's that?
Can you put one variable on the x-axis?
Yeah, you could put y here, and so you could think about the flag being on the ground, and these would be different heights of the flag, and it would still have the same. But we want to think about this as time 0, time starts, and the rate stays constant as the time. Yeah, so you could argue that was y, but it's not really I don't know, convenient, practical, something. I don't know what the word is, but x makes a lot more sense. That would what it would be. Okay, so now check this out. Here's another graph. What's going on in this graph? Is this a height graph? Is this giving us the height of the flag?
It's just more realistic because as he's altering his hands, not that it's lowering.
So you're saying it's a rate graph also?
Yes.
It's still a rate. He's saying it's still a rate graph. Is it a constant rate of change? No. Now it's a rate. It's still a rate graph, but the rate of change is no longer constant. right? And what's happening? So the rate, every so often, the rate seems to go to 0 and then head back to our negative 0.75. And so your theory is?
Well, I mean, it's a person, so as they pull, they're going to start and stop, start and stop. It's just humans aren't constant rates of change.
Right, right. Yeah, pulling a flag means you're gonna yank it down, and then you pause for a second, and then the next hand comes up, and you yank it down again. And so maybe this is a more realistic rate graph for the situation. Okay, so let's talk about what time interval were we talking about? From, was it 0.6
0.6 to 2.4.
to 2.4? And what is that time interval? How do we model that? What symbol do we use for that? dx. I said dx was 2.4 seconds. And with that constant rate of negative 0.75, we easily got the change in height was? Thank you. That's just the final, right? That's the final x. Change in x, 1.8. And so we say that change in y is always negative 0.75 times the change in x. All right, so now let's look at the more realistic situation. Same interval of time, so I want dx of 1.8 seconds. Okay, tell me what the change in y is. Tell me what the change in height is with the more realistic situation. dy equals mdx, right? The rate is changing, right? You change a little bit, like so over here. Change time a little bit, the rate is suddenly different. Can I use dy equals mdx? What's that? We're talking about height. What does area have to do with it? Right? We're talking about height of the flag, right? Who told you it had to do with area? This is about height and time. I'm a different kind of teacher. Yeah.
Wouldn't it be, dy would be the interval
Okay.
of it from 0.4 or 0.6 to 2.4 of
This is still, we're still put time on this axis. We still have time and rate of change, and so we have the same. It's still dx is 1.8. The question is how much does the height of the flag change now? How about this? Is it going to change more or less? Is it going to come down further or come down less far? Less far, because there's a slower negative rate in there. So we don't expect it to come down as far as, what was it, negative 1.35? Was that what it was before?
Yeah.
So maybe, who knows, something like negative 0.8 or negative 0.9 or negative 1.1, but not as much as negative 1.35 meters. But what? So here's the thing. We got a more realistic situation, but suddenly we have a harder problem, right? So it's like the trade-off. You want something better? You got to work harder for it. That's what life is like, right? If you got something less realistic, boom, easy. Constant rate of change, mdx, done. Next problem. Here, changing rate means those bets are off, right? Question here.
Would you calculate dy by multiplying dx of 1.8 seconds by the integral of what the change in y is over that span of time?
But we're pretending we don't know what integrals are.
Oh,
We're starting over. Yeah.
Never mind.
Okay, but it's time to go. So here's what we're going to do. So we need a little bit more to do Monday's homework. So we're gonna continue class with a little more video. It might be like 10 or 15 minutes of video, continuing the same discussion, and then you'll have a worksheet posted on Blackboard that'll be due Monday in class. Okay, on this stuff.